Now, let's go into the implementation and some programming considerations that you need to have in general. So, as with anything else, there are engineering trade-offs in building this 16K memory. It turns out this thing needs to be, highly multi-ported. So if you look at it, 8 of these SPs need to access. Okay, 8 of these SPs need to access the shared memory. Assuming that the shared memory is very fast, okay, you can do one cycle per access. Okay, very fast. Still, it gets a little bit scary. If you know, in the general case, what we would do is we would actually just build a single structure. And we literally have 8 pairs of 8 wires, okay? Sets of wires going into the structure. For every memory storage, we will have 8 of those wires going in, because that's how you can implement a true 8-port access to the memory structure. So let's use one simple example here. Let me see. 1, 2, 3, 4, 5, 6, 7, 8. Okay, there are 8 of these people. They all look very bright. They look, all very, very intelligent. So, let's say I want to use these 8 people to answer my customer phone calls. Okay? And so, for a true 8-port register memory file, what happens is, essentially I put 8 phones in front of each person. Okay, 8 phones. So every person will have 8 phones. And when the customers call, okay, there are 64 phone numbers. Okay, actually 8 phone numbers. So each number will have 8 handsets that go into 8. Okay, so far? So the external interface is such that you have 8 numbers that each customer can call. Okay? And whatever the customer pick will ring on the phone. Okay? And so you can have a situation where, let's say, with those 8 phones on his desk, we can actually have a situation where the customers, when the first customer call the first number, then he picks up the phone. What's your name?
Faisal.
Who is that? Faisal. Okay, Faisal is pick up the phone. ECE 498. What can I do for you, right? And then the second customer who calls that number will see a line busy signal, right? So you will try the second number. So the second number comes in. Ideally, you would like to have Kuang to pick up that call, right? But if I have a true 8-port design, Faisal is going to just pick up the second phone and start to talk to 2 people. Okay? And then the third person will say, oh, you know what, I want to call Faisal. Last time I talked to him, it was really nice. So the third person called, and then so Faisal pick up the third phone, and then this, right? And then the fourth, right? So fifth, right? So you know what, we can have a situation where all the other 7 will be filing their nails and eating sandwiches, and Faisal can actually be here talking to all 8 customers. And this is actually a nice design in the sense that if I have a really, really good customer service agent, and these others are really bright, but they're not just as polite. Okay, that's the thing. Then the customers can still all get to Faisal. Okay? Why is that important? Because if I have all the memory locations, let's say I have a memory structure, I could have a situation where all the accesses from all the processors want to go to the same part of the chip. If I have a true 8-port implementation with 8 sets of wires, 8 handsets in front of the person, I can take care of it. Okay, but it's very expensive. Hiring someone who can talk to 8 people at the same time on 8 handsets with 8 hands, it's very expensive. Okay, so that's why people don't do this in general. And so what people do is people do banked implementation. Essentially, what happens is that in order to support, let's say 8 banks, 8 ports, I actually do something like 16 banks, and I'll talk about why. So these banks, each can only serve one access, okay, at a time. So I really don't have these 8 handset kind of situation. Each person only has one handset in front of him, in this case, right? So now there's only one handset for you, one handset for you, and so on. So when the customer doesn't care, this handset will have a number, right? And this handset will have a number. The first one I call, voice picks up. Okay, the second one calls line busy, so goes to this one, right? Dial a different number, goes here. Third one goes here. Fourth one goes here. So everyone will be talking to a customer at the same time. It has the appearance that we can serve 8 customers at the same time, even though one gets polite treatment and the others get not so polite treatment. Such is life, right? Now, if someone says, I really, really want to talk to Foiza in this situation, okay? So I dial that number, the line is busy, but I remember I got good treatment last time when I talked to Foiza. So what would the person do? Wait. He's not going to dial the second number because Guangwei was not so nice to him last time. Okay? So the second person will be waiting until the first phone call ends, and then the second person gets to call. And the third person calls, line busy. Oh, okay, I'll wait. So you can literally take 8 phone calls. If you really want Foiza, okay, you can take 8 phone calls for all of you to get served by Foiza, right? The situation is very similar here. I will take my 16K. Okay? And I divide them into 16 banks, 1K each. Okay? If my computation is such that SP wants an address, which is in bank 0. SP1 wants to have address, which is in bank 1. SP2 has an address that maps into bank 2. Then everyone can be served at the same time, because each bank can serve one request. As long as your address pattern is such that none of the addresses to be used in the same cycle go to same banks, then you're fine. Okay? However, remember bank 0 will have 1K bytes. Okay? So you can have 256 single precision numbers. If you have a very bad day and all the 8 SPs are issuing addresses that correspond to one of those 256 data elements in bank 0, then you are in bad shape, because that thing will take 8 cycles to serve. Okay, for bank 0 to have 8 cycles to serve. Just like if someone really just wants to talk to Foiza, 8 phone calls. Okay, you need to wait. Now, so this is called bank conflict. Bank conflicts in these kind of memory systems is usually done by stalling the processors. And essentially, the 8 processors are going to all simultaneously generate one address each, right? And all send the address over. There's a piece of hardware mechanism that looks at the parts of the address and figure out very quickly. You don't need to look at all the bits. You only need to look at some bits. And you can quickly figure out that they are all, 2 of them are going to the same bank, or 4 of them going to the same bank, or 8 of them are going to the same bank. Once you figure it out, you stop the processor, okay? And then you start to crank out those data values, okay? And take how many clock cycles it takes to be able to get those data out of these banks. And then you give all the values to the processors and you resume execution. However, time is lost. In this time, the processor could be doing something useful. In this particular design, nobody has told me this. My guess is G80 does not do warp switching during this time. Okay? So you'll be losing clock cycles. Does that make sense? Okay? Even if it does warp switching, it will also take more warps to be able to cover these latencies that you may not have taken into account. Okay? Either way, you will lose something. So let me show you how you can run into these kind of things and how you can avoid some of these things and how you can actually do something. So let's say, what are the situations where you don't have any bank conflict? If you have, let's say, 16 threads running at the same time, all accessing, one accessing one piece of data each, then you will end up, a very good pattern is thread 0 goes to bank 0, thread 1 goes to bank 1. So all the 16 go, directly to a corresponding bank. This is the most trivial case you can see that has good behavior. Turns out this happens very often. The reason is a lot of the algorithms, such as the matrix model, dot product multiplication, right? Dot product, you will be going down the elements, okay? And when you go down the elements, if you use threads to go down the elements, the neighboring threads will be accessing neighboring elements. So you will be able to essentially have all the neighboring threads in a warp accessing neighboring elements, and the neighboring elements will be assigned to the banks as 0, 1, 2, 3, 4, 5, and then wrap around 16, 17, 18, 19. So the data elements are distributed into these banks by laying out the neighboring elements across the banks and then wrap around. Okay? So this is a very typical technique for people to be able to put the elements into these banks in a nice way. And whenever the access pattern is sequential across these threads, then bam, everyone goes to its own bank. Yes?
So just to be clear, if I define a float array of 16 floats, it puts one float in each bank.
Exactly. Yeah. So the array will be literally spread across all the banks. Okay? So that's great. But even in some situations, such as FFT, for example, you will be accessing things across each other, and you're not doing strictly, just sequential access. However, as long as the mapping pattern is such that each of you would eventually end up in a bank, in a different bank, no matter how complex or how simple these mappings are, you will be able to all get your data in one clock cycle. And how is this done? This is done with a crossbar switch. So the hardware will figure out all these the pattern and set all the switches in the crossbar so that all the banks will be connected to the right processors with that switch. Okay, it's a fairly expensive kind of design, but it's pretty standard in industry today. So you could have a two-way bank conflict. And this typically happens when you don't access these data structures in sequential way. That is, somehow you start to skip things. Okay? And one example is, somehow thread 0 access a pair of elements. And then thread 1 access a pair of elements, and so on. Okay? And this happens. It's not as stupid as you would think, because a lot of the vector reduction algorithms do that. You give these reduction, did they do the vector reduction? They did, right? Yeah. So when you do the vector reduction, you will have a huge linear array, and the very natural way of thinking about it is to each one will access a pair of the original elements and then generate a partial sum, right? And then you generate another partial sum, you just do a tree, right? So it's not as stupid as you would think. And the second level of that tree would essentially do a 4 stride and so on, and eventually get to 8 stride. So let's start with a 2-way stride. If you do a 2-way stride, then the first thread is going to be accessing bank 0, while the second one is accessing bank 2, and then the third one will be accessing bank 4, and so on. But you still have all the 16 threads. So thread 8 will be actually will write back and accessing same bank 0. Whenever you have a skipping pattern, sooner or later, the later threads will have to wrap around, right? So whenever it wraps around and you execute at the same time, you have a banking conflict. So in a 16-bank system, if you have a 2-way stride, 2-stride access pattern, you are going to end up with 2 conflicts per bank, and you will have banks that are not used. Okay, just like in the first situation, you will have everyone calling FOISA, but nobody else gets used. Okay, you will have idle banks. And then if you continue this situation, you have stride of 8. You will have dun, dun, and then wrap around, dun, dun, wrap around. So you will end up with 8 of those accesses in the same bank, and you'll be using only 2 banks. If you have stride of 16 and beyond, you'll be only using 1 bank all the time, and you are in bad shape. Okay? Suddenly your execution is 16 times longer than you expected. So how addresses map to banks on the G80? Each bank has a bandwidth of 32-bit per clock cycle. Successive 32-bit words are assigned to successive banks, right? And G80 has 16 banks, so bank is really the address, the remainder when you divide by 16, the least significant 4 bits. How does the hardware detect banking conflict? Does it need to look at all the address bits? All it has to look at is the last 4 bits of each address. And you would be able to tell, right, if they have banking conflicts. So, same as size of a half warp, and no bank conflicts between different half warps, only within a single half warp. So shared memory is as fast as registers if there are no bank conflicts. And the fast case is all the threads of a half warp access different banks, and there is no bank conflict. And all the threads of a half warp access identical addresses, there's no banking conflict. This is an interesting case. Even if they all access the same bank, as long as the location, they are accessing exactly the same location in that bank, then there's a hardware mechanism to broadcast it. Okay? What really gets bad is when you access the same bank but different locations. Okay, that's where the banking conflict happens. The slow case is that multiple threads in the same half warp access the same bank but different locations, and now you must serialize the accesses. The cost is the maximum number of simultaneous accesses to the same bank. Okay. So one of the kind of a common pattern that we're going to be seeing is when you declare these structs, okay, in the shared memory. If you have, let's say, the vector is a struct of 3 variables, okay, and each one is a single precision floating point, then implicitly what happens is every time you load that struct into shared memory, you automatically load 3 locations, 3 consecutive locations, 3 consecutive words. And some of you may not realize that was going on, okay? And even me, when I write some of these programs, if I don't think about it, sometimes I forget about that. And the second one is, you may have a struct that has a float and an int. Okay, so that's two variables, right? And it actually makes a difference. So let's say in the program you declare a vector array of 64 elements, and each element is a struct vector, right? So each element is a 3-word struct. So let's look at, this piece of code here. If we're loading, if each thread loads a vector element into its shared memory, into its shared memory, into a variable here. So vectors is in the shared memory, and by loading that element, you're implicitly loading 3 consecutive words. Okay, and those 3 consecutive words would be, let's say if we started the vector in bank location 0, then those 3 consecutive words will be coming from 3 consecutive banks. Okay, so that's going to be the bank 0, bank 1, and bank 2. So the first thread is going to go to bank 0 for the first element. And each PTX instruction is actually going to just load 1 word from the bank, from 1 word from the array, from the struct into the variable. So even though the CUDA code says we're going to load 3 struct fields into 1 variable, but the PTX code is going to break it down into 3 shared memory loads, each one loading into a register. Okay? So in the first clock cycle, what happens is that thread 0 is going to load from bank 0. Okay? That first load. And thread 1 is actually going to load the first element, the first word of its 3 elements. And that's going to start with bank 3. Okay? Because each struct occupies 3 banks. So the second thread is going to go to the second group, and the third thread is going to go to the third group, which will start with bank 6. So in that first clock cycle, what's going to happen is that you're going to have thread 0 accessing bank 0, thread 1 accessing bank 3, thread 2 accessing bank 6. And it's going to do a 3 increment through all the 16 threads. Because it's an odd number, you're going to be incrementing by 3. So by the time you wrap around, you have bank 15. And when you add 3, you're going to actually go into a different bank, bank 16. So you're actually going to go back to bank 1 rather than bank 0. So if you work out all the access patterns, you're going to see 0, 3, 6, 9, 12, 15. 15, and then 2. Okay, and then 5, and 5 and 8. So these accesses will actually naturally work themselves out in the bank conflict. Okay, so that's a good one. However, if you look at the same thing that was almost the same, when you load from my types, it's a 2-element, it's a 2-field struct. So the same load is going to have a slightly different access behavior. The first one is going to start from bank 0. The thread 1 is going to start with bank 2, as thread 2 is going to start with bank 4. But after you go all the way down, you're going to have bank, so 0, 2, 4, 8, and 14, right? And when you add 2, you go back to 0. So that gives you a 2-way bank conflict because every 8 will bring you back to bank 0, and the 16 threads will have pairwise conflicts in those even number things. So this is something that after you think about it a little bit, it's not a huge deal. It's not so complex. But without thinking about it, sometimes just by looking at the code, you may not immediately realize that this is what's going on. Okay? There are some common array bank patterns that cause conflicts. Okay, so let's go into this one-dimensional array access pattern. A very obvious access pattern is if every thread, if threads are going to access every other array element, that's called stripe one access, right? So if the first thread is going to access thread element 0, and the second thread 0 is going to access element 0, thread 1 is going to access element 2, then you just skip 1 in every access, then you will surely run into this conflict. But oftentimes people fall into that kind of a pitfall because they're actually doing something that is not necessarily skipping in their mind. They're actually doing some kind of, let's say, reduction computation that they will take a very large vector and they need to get, let's say, the sum of all the vector elements. And by doing so, a very natural tendency is to go through the following access patterns. I actually drew up a little bit picture this morning. Hopefully it would help the understanding of this thing. So let's say I have a very large array, okay? Let's say thousands and thousands of elements. And I need to come up with the total sum of all the elements. A very, a natural tendency is to do a kind of a tree-style reduction, okay? Because every time you do a tree-style reduction, you actually have a very, you can do a parallel reduction, and in the first iteration, all the threads will sum up 2 elements. So by the time you are done with that first iteration, you will end up with only, it will end up with half of the elements left. You already sum up pairwise, so you have, partial sum of n over 2, a partial sum. And then you will do another iteration where you would add 2 partial sums together in each computation. So this is a very powerful scheme because you're doing a log style computing, and for n elements you only need to have log n number of iterations before you're done, and you're using a lot of the parallel computing resources to do that summation. So this is good, but usually when we think about this kind of computation, we will say, well, you know what, I'm going to have each thread to add 2 neighboring elements, okay? And there's nothing wrong with that. And then we'll add 2 neighboring partial sums, and we'll then add 2 neighboring partial sums until everything becomes only 1. And that's when I'm done, okay? So in the CPU world, this is actually a very, very good approach. In the CPU world, this is actually a very, very good approach. Because what happens is these threads in the CPU tend to run in these different, CPU nodes with cache coherence protocol going on. Okay, for those of you who study computer architecture, the typical CPU multi-core chips will have each core with a private, essentially a cache memory. And the cache memories among these cores will have a coherence protocol that keep each other consistent with each other. So whenever you need to do this kind of computation, you will need to actually take into account what we call the cache line size. Because every CPU data is not just stored in its own location. It's actually stored as part of a cache. And that cache line is going to contain several consecutive memory locations. So whenever we compute, let's go back to that picture. whenever we are running a thread to do a computation, we want to have the two inputs of that thread to come from two consecutive locations whenever it's possible, because that will reduce the interactions across these different caches. If thread 1 uses a piece of data that shares a cache, and thread 2 uses a piece of data next to it, then both threads and both CPU cores will end up with that same cache line, and part of that used by one and part of used by the other. And oftentimes you need to also keep them coordinated, you need to keep them consistent, and that will create more and more cache coherence traffic. So when people tune program for these CPU multi-core chips, one of the best strategies in doing this computation is to have each thread to sum up what? The consecutive locations, okay? And so you would chunk up one consecutive location for thread 1, you would chunk up another consecutive set of locations for thread 2. So this will be a very, very natural computation pattern for people who think about these things from the CPU point of view. However, in the GPU, in G80, this is exactly the wrong thing to do. So let's say I have a very large what happens is that when you have those two consecutive locations, and I need to come up with a total sum. In that first step, all the threads are very access natural occasions. Is need to do a kind of a tree style reduction for that first step. Because every time, and then they just all go to the other, actually have a very access their second level with the sum, and then you immediately create another first iteration. Oh, that's not bad. Two-way conflict is maybe not bad. And then the next step will end up with this situation. It will end up with during that first cycle, all the threads are going to be accessing n over 2. Each thread is going to compute. And then you will do another location iteration not exactly nearby, but actually one part. So these two locations. So this is by the first thread, and the third and the fourth partial sum will be accessed by the second thread. So now you have a four-way conflict because the access pattern number of iterations. 0 for the first thread, you're using 4 for the second thread, and leaving resources to do that. So you can, if you continue to do this, remember you're going to have usually when we talk about that computation, actually say, well, you know what, I'm going to have each thread to add 2 neighboring elements. And you're going to be waiting and waiting. There's nothing wrong with that. And then we'll add 2 neighboring partial sums, and we'll then add 2 neighboring partial sums until everything becomes only 1. And that's when I'm done. Okay? So in the CPU world, this is actually a very, very good approach. So instead of doing that, you would. The better access pattern for this machine is going to be, each thread in that first step still going to add 2 elements together. But the elements will come from a slightly different arrangement. That first element being added up for all the 16 threads should come from 16, should just come from, each one should be coming from an adjacent location. So the first element of every thread is going to come from these adjacent locations. And then you just add a big offset, okay, to the second, a big offset to the to get that second element. So the first the thread is going to actually add up element 0 and element 16 into a partial sum. So that when the first access to the shared memory, there's no bank conflict, and then the second access for the second input would not have no banking conflict. Okay? And you can continue to do this all the way until you reach the very end. And it turns out that when you reach the very end, you're not going to have banking conflict either, especially as long as you just keep reducing them into consecutive locations. So that's how. If you look at the library implementation, there are all these library codes from NVIDIA, on vector reduction and so on. If you look into those codes, you will see similar access patterns. Okay, these are the kind of things that people pay attention to in order to get the highest performance code out of the. So another interesting thing, which is going to be a little bit more difficult to visualize, and I'm going to take a little bit more time to go through. I think we went through that a little bit too fast last semester, so I'll try to do better this time. Is if you actually have a two-dimensional data structure in the shared memory, then oftentimes you need to be very careful about some implicit access patterns that you may or may not be aware of that will cause banking conflicts. Okay? So let's say if we loaded a 16 by 16 two-dimensional array into the shared memory, which is the case in our matrix multiplication. Okay? But let's say the computation is slightly different. In this particular situation, let's say we're just loading one matrix. Okay, so let's not worry about two for now. Just say we're doing one matrix. And the computation is such that each thread will process a row. Okay, so thread 1 is going to process row 1 all the way from left to right, and thread 2 is going to process row 2 from left to right. So remember, this is SPMD program. So all of them are executing the same code. And the warps are the threads with consecutive numbers, right? So what's going to happen in this particular piece of code, as you have these threads walking through these adjacent rows together, the first step is that all the threads are going to be accessing column 0. Okay, different elements of column 0. And the next iteration, they're going to be accessing all the elements of column 1. Make sense? So those are the iterations of each thread, right? They're all walking through these rows. But at every iteration, they're going to be accessing the same elements from the same column. And for a 16 by 16 array, unfortunately, all these elements are exactly what? 16 apart in the shared memory. And that's a bad situation. Okay? All the 16 threads are going to be landing on the same bank, and they're asking for different elements. Okay? So it will take 16 of those hardware iterations to serve all the accesses. So there are several very common solutions. And one is you can pad the rows, and you can actually add one element into each row, so that each row is no longer, you can add one element into. Let's see. So each one is 16, and then each one is now 17 elements. Wait. Yes. So essentially, what you're going to do is you're going to actually have 17 elements in each row, and then when you access the elements, in fact, this is not a very good picture, because what I should have shown is that there will be a 16 here, and then you will start 16. So each one, even though you're still accessing the same element of the row, because of that extra element in each row, you will end up in a different physical location for every element in that same column. You're going to see a tilt in the picture. So remind me to update that picture. So when we walk through that same, all the threads are accessing these different rows. As they access the zeros column of all the rows, they will be tilted in the hardware so that they will be accessing a different row, different bank. So that's by adding, one element to each row, and that's called padding. And another solution to do this, intuitive solution that people often suggest, is that you can transpose the matrix. You can, if you know that you're going to be accessing one thread is going to be accessing a row each, then what you can do is you can transpose the matrix so that they will end up accessing the columns. As they access the columns, they will be walking through consecutive locations in a row, right? And that will not cause any bank conflict. There are pros and cons of each approach. The pro of the benefit of the second approach is that you don't need to waste storage resources, because you will end up using 17 elements in each row to store only 16 elements. So usually that's not a very desirable situation, especially when the storage becomes scarce. But the problem with the transpose approach is that you will end up having to do that pre-adjustment. And you are actually going to suffer banking conflict when you do that transpose, because you still need to get the data out of it, right? So you can still suffer banking conflict in that transpose operation. But if you will end up doing multiple passes through your data, in your computation, then it may be worthwhile to suffer once, and then you just can be home free for all the subsequent iterations. So in general, this is one of the areas that will probably have some architectural change in the future. As it turns out that this is not a new problem. Okay? And people in computer architecture know of this problem for at least 30 years. And a lot of the people in 1980s, this particular university worked on different ways of building hardware so that you don't have banking conflict. And one of the most popular approaches that industry uses today is randomized banking address assignment. So essentially, the address patterns get somewhat scrambled before they get placed into these banks. And I don't know, nobody told me anything, I don't know about anything, but chances are, in the next generations, there will be probably that kind of hardware in the shared memory design, so that you don't need to worry about either of these two. However, for this semester, as you work on projects, we got what we got. Okay, we have a piece of hardware that will have this kind of artifact. So you will need to be aware of it, and if your algorithm will end up doing this kind of traversal through the array, either 1D or 2D, doing a reduction or doing some kind of 2D traversal, you will need to be aware of the situation. Let's go back to matrix multiplication, since that's what you're going to be worried about for a while. So the question is, do we have bank conflict in matrix multiplication? So this is something that actually, when I first took my training course at NVIDIA, it was something that it actually took me a little while to think through. You guys probably just got it right away, but it took me a while to these are young and smart people. But it was not immediately clear to me that there was conflict or no conflict. I had to actually play with it a little bit to figure it out. So this is how I look at it. So when you have matrix multiplication, what happens is you load an M array and N array into shared memory, right? So this is the 2D situation, right? You loaded two 16 by 16, okay, arrays into the shared memory. So then the question is, do we have a situation where all the threads are walking through the rows simultaneously. Okay? And the answer is actually no. When we do the matrix multiplication, what happens is that in the innermost loop, in the warp, what happens is you actually have the threads all walking through the same row. Okay, they're not walking through different rows. They're all walking through the same row, but different columns. Okay, in doing that matrix multiplication. You could write your code in such a way that you can do the other way around. And don't do that. Okay, don't do that in this machine. You could change it. Okay. So if you just follow the current way of doing this, then you will have all the threads in a warp all accessing this, let's say, starting with the same 0th row, but they will all accessing different columns. Okay, and in fact, in the warps, there will be consecutive columns. Okay, so if you look at the access pattern for M array, because all the warps are going through the same row, they are all accessing the same value, the same variable from the same bank. It's just that you need that variable in 16 different threads. So this is actually not a bad access pattern for shared memory. You can go into the same bank as long as you're looking for the same value. Okay? And what you really start to get into trouble is when you go to the same bank for different values. So this one is actually a very nice broadcast. For every iteration, 0th element will be broadcast to 16, and then 1 will be broadcast to 16. And if you look at the N array access, what happens is in every iteration, there will be elements from different column locations, okay, adjacent column locations being accessed by adjacent threads. So all the threads in the warp will access the first 16 elements in that top row in the first round of access. And then it will go down to the second row, the third row. So that's no banking conflict. This is a perfect sequential mapping. Okay? So that's why in either case, you're not going to see any shared memory bank conflict, even though the computation sounded a little bit like the previous example. Okay? And this is the reason why we always did these lectures. We wanted to just teach you some of these somewhat subtle differences that can lead into big performance differences ahead of time. This is not, instead of having you to walk into these things and then eventually get tripped a couple of times and then you say, now I see, right? So in many ways, the lectures, the next couple of lectures, the previous lecture and the next couple of lectures all have to do with some common pitfalls that unless you have seen this before, unless you have a little bit of a framework to think about it, you can get confused for a long time, and then eventually you will get it. It's not rocket science. Okay, all of you will get it. It's just that it will take a much longer time for you to actually get through it than if we took you through it. And my expectation is after I taught, after David and I taught you these, patterns and pitfalls, at some point you will build up enough intuition that whenever you see a situation that doesn't smell good, you'll know right away. Okay, and that's the difference between a seasoned programmer and a green programmer. Both can be very smart, but both can be very good. So let me give you one sort of interesting anecdote. So I always felt that these dealers are overpriced. Okay, so when you fix a car, when you bring it to the dealership, you always felt that they overcharge you, right? So I always like to go to some of these local car places to get my car fixed whenever possible. So the other day I ran into a very interesting problem. So my car just immediately, my engine shuts down right after I reach speed of 50. Okay, and When I ramp up to 50, boom, engine shuts down. And that happens on freeways, right? So it's not a good thing, right? So, I took it to one of the local shops. And, they look at it, and the mechanic is actually very talented, I like him a lot. So, he looked at it and he found like 6 different problems, okay? And so he said, I don't know for sure whether it's one of those 6, but all of the 6 of them have the potential of causing the problem that you have. So I said, how much does it cost? He said, oh yeah, it costs about $500 to fix that. Okay, fine. So just zap them all. So after I fixed it, it did run very smoothly. Okay, it did run very nice. But when I reached 50, still shuts down. Okay. So he did fix 6 problems, and the car did run better, but the problem didn't go away. So at that point, I realized that I need to go to a place where people have seen more of this particular type of car, and people who probably have access to a database that national database that has similar problems. So I brought it into the dealership, and the mechanic just look at the national database and say, "Oh yeah, it's just a distributor. It's a somewhat rare but not a known problem in the distributor. So it will take you $200 and we'll fix it, right?" So that's exactly what it is, okay? And you are tapping into the experience that a lot of these other people have built up over time, and that's called patterns, okay? And we have object-oriented programming patterns and parallel programming patterns. And this is sort of an introduction of parallel programming patterns for these machines. People have spent time struggling with these things. People have spent time debugging performance issues, and people have been spending time scratching their head trying to figure out, and people have been spending their time fixing 6 problems that are not exactly what they're trying to fix, okay? So with this kind of information, you will be able to do a lot better, a lot faster. So this leads into the remaining 2 things that I'm going to try to talk about today before I let you go. One is, sort of the whole issue of tolerating memory latency, especially long memory latencies. It turns out that global memory access is by default low latency access. Whenever you try to load something from global memory into shared memory, that load is going to be a low latency load. Okay, so you know that. There's no way around it. And even in some cases, and some of you will be using something called a texture memory, and that thing is cached. So some of the accesses will be long latency, but most of the accesses will be shorter latency. But even in that case, the texture cache is going to have slightly longer latency than shared memory access. So you will still have some latency that you need to deal with. So a very typical way of dealing with memory latency is to have lots and lots of threads, as we have explained so far. If you have lots and lots of warps that can go instead of a current warp, whenever the current warp does a low memory access latency and use that variable, then you can switch to a different warp. However, as we explained before, you will have lots and lots of these warps in each one. So if each warp is capable of tolerating, let's say, 4 more cycles of memory latency, because of the number of warps that you have available, you will be able to to use whenever you use 4 more, you can tolerate 4 more cycles of latency in each warp, you can end up needing much fewer number of warps. And that's a very useful situation when the warps or the threads use up so much resources, such as registers, that you cannot fit more registers into these, fit more warps into these SMs. So one typical way of doing this is to use the load to hide, a low latency. So for example, if you have load 0, and then you use load 0, you have load 1, you use load 1. If you look at the actual machine code, the compiler would have reordered these instructions in such a way that it becomes, you'll do load 0 and you do load 1, and then you do the, you will take, to use the mathematics operation to consume load 0 result, followed by the mathematical operation that will consume loop 1. And when I first looked at this piece of code, before I built up my intuition, I said, what kind of difference can this make? Okay, this is not going to make too much difference. It's just one instruction. It's not just one instruction. It's one instruction that will take 4 cycles to process for each warp. Okay, and there are, so for each warp, 4 cycles, you can end up with half of the warps that you need, because you typically will have 10s of these warps, or even 20s or 30s of these warps. So having 4 additional cycles worth of ability to tolerate latency, given 16 of these warps, you can actually increase the tolerance by 64. Okay, and that's a very big number. And so it's something that can be very, very significant effect. And the compiler does handle this. If you look at the code, the compiler actually handles this kind of situation very well. But you must have enough non-dependent loads and math. So one typical example is that in each loop iteration, you may just have a load and you have a compute. So let's say you're writing a piece of code that, a loop where in each iteration you only have one load and one compute. So tell me how you will be able to get a better situation like this. How do you expect that? If you only have one load and one compute, where do you find a second load? Can't, right? However, if you unroll the loop, okay, if you unroll the loop, so you have, essentially instead of looping from 1 to 100, you replicate the loop body so that you will do 2 iterations in each loop body, but then you iterate only 50 times. You iterate half of the number of total times. Then suddenly you have load and compute from that first iteration and load and compute from the second iteration. Now you can actually do the overlap. The compiler does not do automatic loop enrolling at this point. It will probably do in the future. And primarily because loop enrolling is not a very hard thing to do in terms of mechanics, but it's a very hard thing to do in terms of decision. You will need to figure out how many times to replicate a loop body, and that's an art at this point. So the compiler can actually do a reasonable job, for a lot of the code, but occasionally it will mess up and it will create a bad situation. So that's why, the production compiler that you're using today does not do a lot of loop enrolling, and you will need to make that decision. And that will change eventually, in the future. But for this semester, you will still need to, do some of that by hand.